Well, yeah, so you, I mean,
position.
if it were, this is,
Emmanuel Breuillard is going to tell us how to generate a nice hyperbolic element. This has a question mark, and his title on the things doesn't. So I wonder what that means.
I don't know. So thanks for the invitation. It's a pleasure to speak here. I'm going to speak about some work which was done here at the Institute during this program. Although the question that started this, so I realized that something is missing on this page, that this is entirely a joint work with Koji Fujiwara, and I was about to say that the question that started this is a question we asked each other 10 years ago at a conference that David reminded me was organized in Hawaii by David and Eric. So finally we basically managed to answer it. So that's what I'm going to tell you today. So here's the general setup. So you start with a group and a finite subset of the group, and you look at S to the n. That's the set of products of length n in with letters in S. So here is a very general problem, vague problem. So for example, this is a question which was addressed by Michael de La Salle at the beginning of the week. So suppose that you have a group, you want to know the group by just knowing some part of the k-graph. Okay, so that's a very, very general problem. I won't really be talking about this, but it's just to set ideas. The idea being that we try to quantify things, so we try to understand what's happening, to be able to tell global properties from local properties. So for example, suppose that your group contains some nice elements. So I will say what nice means. Then can you find them already in a small ball in the k-graph? And have a control of how small or how large this radius is. So for another similar question is, you look at the growth of S to the n. So you suppose that your group acts on a nice space, look at an orbit, and look at the rate of growth of this orbit, or just the rate of growth of S to the n. Suppose it grows at a certain rate, then is it true that you can actually already that already there is some individual some element g in S which is itself responsible for the growth, so its powers are responsible for the growth, and we'll see that this property holds in many cases. So this is so this means, suppose you have a long word that reaches some place in the space, then in fact if you have a word, so if you can reach this point with a word, a non-commutative word in elements in S, then in fact there is a single element in S which can reach just as far by taking its powers. So this is the problem. So so this an instance of this problem appeared long ago in the solution to the Hilbert's fifth problem by Gleason and Yamabe in the 50s. And so somehow if you have to remember one thing about the proof of the Gleason-Yamabe theorem on the structure theorem for locally compact groups, it's just this. It's this Gleason lemma, which essentially says something that amounts to what I just said before, that the growth of a word can be reproduced by the growth of one power. So let me just explain this. Gleason showed, so somehow the proof of the Hilbert's fifth problem is split into three parts basically. So the first part is due to Gleason. He showed that NSS groups are Lie groups the second part to Yamabe, he showed that locally compact groups can be are projective limits of NSS groups, and Montgomery-Zippin showed that when you act on a manifold, then you have to be a Lie group. So, so the setting is this. So suppose U is a compact neighborhood of the identity in a group, in a locally compact group G, and for a subset S in U, I'm going to define this number. So it's the length. So yeah, it's the first n for which S to the n pops out of U. Okay, so you have maybe this picture. So you have U, the identity here, and you have some set S, and you start taking words in S, and at some point, so you look at S squared, maybe, and then somehow S to the n. You look at the first n for which it pops out of this U. Okay. So clearly, if I take any element G in S, then you know, if I can, if the powers of G escape U at some time n, then of course there is a word in the elements of S that escape U at time n. So n U of G is bigger than n U of S by obviously. And Gleason's lemma says that the opposite inequality holds. So it says that if your group is NSS, then there exists a constant depending on the neighborhood with the property that given any subset S in U, you can always find an element inside with this property. Okay? So note that if you have a connected Lie group, then this is obvious because you have the exponential map. So everything, you know, near the identity, everything looks like a neighborhood of the identity in a vector space. So it's just you have a norm on the vector space, so you understand what's going on. Okay, but this is the key lemma, and from this you can, I mean, Gleason was able to push this to show that the space of one-parameter subgroups has a nice additive structure, and therefore is a vector space, and it's locally compact, so it has to be finite dimensional, and therefore then he showed that NSS groups have to be finite dimensional Lie groups. Okay. All right. So a year later, Yamabe extended Gleason's lemma to general locally compact groups, and eventually showed the structure theorem that you know, every locally compact group has an open subgroup which can be approximated by Lie groups. So you can find small normal compact subgroup modulo which you become a Lie group, and an immediate consequence of Yamabe's lemma is for example this lemma, which is also of the same flavor, which is a consequence. So you see that if you look at this identity, you see that if yeah, so that if n of U of G is infinite, then n U of S is infinite in particular. So this means that if you are not entirely contained in U, so if you escape U, then in fact the group generated by all the elements G in S, yeah, so it's a subgroup trapping property. Then there is a G in S which so the cyclic subgroup escapes U. So in other words, if you look at the group generated by all cyclic subgroups contained in U, then it's already contained in U. Okay, so that's okay. So now, so this was just a way to illustrate this kind of question I want to study in this talk. So here's another example coming from geometry, where it's an example of a similar kind. So suppose you have, so this is a famous lemma of Serre for groups acting on trees. Suppose you have two isometries of a tree, and they don't have a common fixed point, then, so this means, yeah, the group generated by them does not fix a point. Then you can say that already AB or AB has no individual fixed point. Okay. So you cannot say that A, so it could very well be that you have A and B both have a fixed point, so they generate elliptic elements, each of them, they are elliptic, so, but they don't have a common fixed point. Of course, this can happen. Okay. However, if A and B don't have a common fixed point, then this lemma says that the product will have no fixed point. So the product will act like a nice hyperbolic translation. An immediate corollary of Serre's lemma is that a torsion group, a group all of whose elements have finite order, must have a global fixed point when it acts on a tree. Yeah, finite. I should have said finite generator. Yeah, of course. Yeah, thank you. So, if you look at the case of SL2, for example, SL2C, then it can happen. Then, for example, like in Alan Reed's lecture, it can happen that AB and AB are elliptic. But then, if they don't have a common fixed point, then you can show that the commutator is hyperbolic or loxodromic. Okay? So here by elliptic, actually, I just mean that the eigenvalues have absolute value 1. Okay. So the proof of this is just a simple 2 by 2 matrix computation. Okay. But this means that very quickly you get out of elliptic elements. Okay. So let's look at this problem a bit more thoroughly. So suppose you have a group acting on a space, and you have okay, I'm only talking about finitely generated groups. So you have a finite set generating a group, and and you assume that the finite set is made of elliptic elements. They all fix a point. And then you take products, and you would like to escape elliptic elements. So how can you? The question is, can you always escape elliptic elements? So yeah. So first question is: suppose the whole group is made entirely of elliptic elements. Each of them fix a point. The question is: does this imply that G has a global fixed point? Okay. And gamma, sorry. Gamma, okay. So, yeah. So in Euclidean space, it's not true. So it's true in R2, it's true in R3. But in R4, you have a counterexample. Namely, you have a finitely generated group which consists only of rotations, pure rotations, but it doesn't have a global fixed point. Okay, now 4. And so the first example is due to Bass in a paper in the 80s answering a question of Kaplansky at the time. And the idea is you just take two rotations, but with different fixed points and acting on C2, with the linear part being in SU2 in such a way that they generate a free group. And so if they generate a free group, then you see that the 1 is never an eigenvalue. So you're never going to get a skew rotation, for example. So a skew translation. So you have all the elements of the group generated by A and B are pure rotations, but they don't have a global fixed point. Now, what happens if you don't take a billion, like a Euclidean space, but you take a symmetric space? For a symmetric space, the answer is yes. So there is a global fixed point. Yeah, so namely, if you have a group, all of whose elements are elliptic, then there is a global fixed point, either on X or on the boundary. And when you have a Boatitz building, then in fact there is a global fixed point in the building. And this is a nice paper of Anne Parot. So there's no geometric proof of this somehow. The proof is by linear algebra. So the proof is you prove this proposition. So suppose you have some finite set S in GLDR, generating a group all of whose elements are elliptic. By elliptic I mean all eigenvalues are mod of modulus 1. Then you can be simultaneously conjugated in a block triangular matrix in a simultaneously block triangular form where the blocks are contained in some compact orthogonal group. Okay, so in particular, if you are acting irreducibly on RD, then you must be conjugate inside SOD. Okay, so that's somehow yeah. So the point of this, the proof of this proposition is essentially this Burnside lemma that you can express the trace. You show that the trace of these elements are all bounded, and this implies that the group is bounded if you act reducibly. So the basic question is this. So can you somehow quantify this lemma, this proposition? Can you show that you can, if you contain a non-elliptic element, can you find a non-elliptic element quickly? So that's the question. So is there n such that if gamma contains a non-elliptic element, then s to the n already contains one? And the answer is a bit surprising. So the answer is no, there isn't such an n if X is a symmetric space. And the answer is yes if your Breuillard is building. So you mean, so I put a comment here that this proposition does not hold when, so this means somehow, the fact that the answer is no here means that this proposition here does not hold if you replace the real field by a real closed field like the ultra product of the ultra power of R, or like these Robinson fields that Mark Burger likes to talk about recently. So the reason is, so you can find such an, because of this counterexample, there are subgroups of GLD of R bar, where R bar is this ultra power, which are entirely made of elliptic elements, but they are not conjugated inside some SOD. So they do not preserve a quadratic form, positive definite quadratic form. Okay, so this I'll explain in a moment where it comes from.
So you said that for building it's yes. So how big is this n?
Yeah, so it's like this.
Oh, it's
Some big O, yeah, it's like the dimension. It's basically, if you're in GLD, D squared is enough. Okay. And yeah. So this has to, this can be contrasted, or there is a, there's a big difference between elliptic and torsion, and in the context of linear groups. So indeed, for linear groups, we have this effective Schur theorem. So Schur, in the early 20th century, showed that finitely generated torsion linear groups must be finite. Okay. So the question is, so in particular, if you generate an infinite, if you have a set of matrices and you look the group it generates, if it generates an infinite group, then there will be an element of infinite order in that group. Okay, so following the philosophy I outlined at the beginning, the natural question is, how far do you need to go to find this element of infinite order? And the answer is, this is bounded. For linear groups, it does not matter what set of matrices you choose here. It's always going to be bounded by some n of d, depending only on d. Okay, so you can always escape torsion elements, but you can. So, but the proof, the proof uses some number theory, because so you can have. The problem is you need to, the roots of unity have, can be of very large order, and you want to have a bound independent of the degree of the field that number field that you look at. And indeed, in fact, this n of d must tend to infinity, and there is a nice example if you take the Grigor-True group, and it has like a torsion Grigor-True group, then you can see that if you chop the presentation after a while, this group becomes virtually a product of three groups, so it's linear, and it has a very large torsion ball. So you can certainly find elements with, matrices with very large torsion balls, even though they are infinite linear groups. But of course, the dimension of the size of the matrix has to grow, has to be very big. Okay. So I promised why cannot you escape elliptic elements? So here is a counterexample. So it works in certain symmetric spaces and not in others. So if you, so it's a fairly simple-minded example, but you take a symmetric space G mod K, and you take one such that the elliptic elements in G are Zariski dense. So the elliptic elements, your elliptic means that the eigenvalues have modulus 1. It's actually a set which is definable in real algebraic geometry. So Zariski dense here is actually equivalent to have non-empty interior. And this happens, for example, for SO2 and 1. So the idea is you pick A and B in the compact group, which generate a free subgroup in such a way that none of the elements in this free group have 1 as an eigenvalue. So this can be achieved using a theorem of Borel and Larsen, a very nice theorem about word maps, that if you have a word map on an algebraic semi-simple Lie group, then it has to be dominant. So namely, the image of a word map from G cross G to G is Zariski dense. Okay? Image of a word map is Zariski dense. So so using this, you can make sure that the eigenvalue 1 never appears. And then you see that if you wiggle a little bit your two elements, they generate a subgroup of the compact group. But if you wiggle them a little bit, they will generate a Zariski dense subgroup of the ambient semi-simple Lie group G. But because you wiggle them just a little bit, then for a long time, all the words in this new A prime and B prime will remain very close to the words in A and B. And because we know that 1 is not an eigenvalue, then we know that the fact that 1 is not an eigenvalue means somehow that you lie in the interior of the elliptic elements. So all the small words will still be in the interior of the elliptic elements, and so this means that for a long while, the whole ball in the Kähler graph of very large radius in A prime and B prime will be made of elliptic elements. However, the group is Zariski dense, so there will be at some point you will find some non-elliptic elements. Okay, so you can't, of course, you can't do this in SL2C because we saw before that you have this property, right? In SL2C, if you cannot have A, B, and the commutator being elliptic, that can't happen. Okay, so but SL2C is not the elliptic elements are not they have empty interior, so that's why. And and so actually that's a remark. So if the symmetric space has the opposite property, that the elliptic elements are not Zariski dense, then you can escape elliptic elements. And this is due to a general phenomenon which in this context probably first arose in a nice paper of Eskin, Moses, which is the escape from subvariety. So if you have a variety, a proper algebraic variety of a semi-simple algebraic group G, then you can always escape it by look at the powers of this set S. it will always get, at some point, will move out of the algebraic variety in bounded time, and the bound depends only on the variety. Okay, so this can be proved. Some bounds can be proved on n of v using Bézout theorem, but if you think in terms of ultra products, this is somehow completely obvious that such a bound should exist. And that's a remark here. So elliptic elements are not Zariski dense if and only if the absolute rank of G is strictly bigger than the absolute rank of K. And if you remember Nikolai Nikolov's talk this week, in fact, this is if and only if the Betti numbers of the L2 Betti numbers of X are 0. Okay, so certain symmetric space are like that. SLN is not like that, but SO2PQ is like that, for example. Okay, so that's it. So we cannot escape elliptic elements. Fine, but maybe we can still show that something rose. Okay, we can't escape elliptics, but okay, maybe we can still have some luck. So. And this brings me to another subject, which is the subject of the joint spectral radius. So, so if you stop listening, you can listen again now, because it's a different subject, slightly different. So, in the 60s, Rota and Strang, this is Giancarlo Rota, and so they are both, I think, MIT mathematicians at the time. They introduced this notion of joint spectral radius of a set of matrices. So they were not interested in groups, just matrices. So let's say in the ring of matrices, and you take an operator norm on the ring, and you consider this quantity, which is the asymptotic rate of growth of the powers of S to the n, of all products. Okay. So, right. So the norm of S here is the maximum operator norm of an element in S. So this notion has been studied a lot in recent decades. So in connection to wavelets, and a lot of really a lot of literature on this. In the applied math community. But most notably, Mark Berger and Wang showed in 1993 the following spectral radius formula. So they showed that the joint spectral radius actually is equal to the rate of growth of the maximal eigenvalue of an element of a word, S to the n. So there is an obvious inequality that R of S is always at least this lambda infinity, but they showed it's the same. Okay, that's very general. Okay, this generalizes the the Gelfand classical linear algebra formula that the maximal eigenvalue of a matrix is equal to the exponential growth rate of its powers. Okay, so it's a generalization to several matrices. Okay, so this means that the maximal norm of a word of length n with letters in S is of the same magnitude as the maximal eigenvalue of a word of length n. Okay. And here note that when you say that, so suppose you are in GLN, then to say that R of S is equal to 1 is basically the same thing as to say that the group generated by S is made of elliptic elements. And so it's the same as to say that you fix a point, or you are conjugated in the upper triangular form with compact diagonal blocks. So about 15 years ago, Bocchi, who is a dynamicist, showed the following very nice improvement on the Berger-Wang inequality, equality, the Berger-Wang formula. He showed that if you're looking at the spectral radius, the joint spectral radius, then in fact this this Berger-Wang formula almost holds already after a bounded number of steps. So there is some k of d less than 2 to the d, depending so only on the d, the size of the matrix, such that for every finite set, the spectral radius is bounded below, so this is always true, but the main point is the second inequality here. So you can find, this means that you can find a word of length at most k of d in letters in S, whose eigenvalue is just as good as the joint spectral radius. But there is a constant here. The constant is c, and it depends on d. Okay. From this inequality, so you see it's obvious that the spectral radius of S to the n is the spectral radius of S to the power n. So if you replace S here by S to the n and let n to infinity, you immediately recover the Berger-Wang equality. Okay. So this is a quantified version of Berger and Wang. And the proof uses is both some linear algebra and some algebraic considerations, in particular Prochési's theorem that if the space, the ring of invariant polynomials in several matrices is generated by the traces of short words, and it also uses some topological considerations and a bit of geometric invariant theory. So, all right, it's not a geometric proof, and I would like today to tell you how to define all these things geometrically. Okay. And at the end I will give some applications to uniform growth. So here xd is a metric space. Now G is the isometric group of X. Then you can, in the same way as we define this joint spectral radius, you can define what I would call the joint minimal displacement of S. So this is a classical thing. It's been used many times in geometric group theory. Maybe not with this name, but okay. So you pick a point X and you look at the maximal displacement of an element of isometry S in S, and you minimize over all points in your space. Okay. So I call this the joint minimal displacement. And you can also all define an asymptotic version, a bit like in the definition of this joint spectral radius. You can take S to the n, look at the joint minimal displacement, we normalize by n, and the limit exists always. You can see that this thing here is always a subadditive function of n, so limit exists. It's equal to the infimum. It's valid for all x. And I call this the asymptotic joint displacement. Okay, so it's sort of measures how far the orbits, how big the orbits, you know, what's the size of the, what's the radius of the smallest ball that contains the part of the orbit up to the image of x by the ball of radius n in your Cayley graph. Okay. On the other side, on the eigenvalue side, then you can define similarly a translation length. So if you have a singleton G, then you can define this quantity here, which is the maximum of the translation length, individual translation lengths of your elements in S. Okay. So for example, if you have elliptic elements, then they have 0 translation length. So that lambda of S is equal to 0. Okay. This is there is some obvious inequalities less than capital L of S, this joint minimal displacement, and because I don't want to just look at the element of S, but I allow myself to take short words in the elements of S. I want to look also at lambda sub k of S, which is this. We normalize by 1 over j to make it somehow homogeneous and uniform. And then you have this proposition, which is very general. It holds in every metric space, every finite set of isometries. The maximum of the translation length of S is at most lambda sub k of S, is at most lambda infinity. So lambda infinity is the limit when k equals infinity here. And this is always less or equal, so this is a crucial bit here. It's always at most the asymptotic joint displacement. Okay. So this is very general, just basically abstract nonsense. It tells you that. Very valid for every metric space. How do you recover the joint spectral radius from this? So, for example, if you take the symmetric space of SLDR, then you take, so instead of taking the usual cat0 norm or cat0 metric, you take the norm metric given by the log of the operator norm of G inverse times H. This is one of those norms that Anne Parot was talking about in her talk when she was looking at Finsler norms. And then for this particular choice of norm, the joint spectral radius, the log of the joint spectral radius of Rota and Strang is equal to this joint minimal displacement. And then the Berger-Wang equality, which you remember from the previous slide, is exactly saying that you have this equality between lambda infinity and L of S. So you have equality here. Okay? All right. So it's very natural to ask for which metric spaces do you have equality? Do you always have equality between lambda infinity and L of S? So before I go there, let me just make some small remarks. The first is that this quantity L of S, L of Sx, so this L of Sx has been studied a lot in geometry and geometry group theory in relation with harmonic maps. Because this is the way to build harmonic maps, is to from the Cayley graph generated by S to a target space like X. The way is to minimize this LSX. So usually people don't minimize this one, but they minimize the L2 version of it. So instead of taking the max norm over S, I take the sum over S of the square of the displacement, and this is, people call this the energy. And when you minimize the energy, you get a harmonic map. So this is just a remark. Another place where this quantity shows up is the study of fine isometric actions on Hilbert spaces. So if X is a Hilbert space, then the action, you have a group acting on the Hilbert space by isometries. Then it gives, then you have a cocycle, and you have this notion of reduced cohomology, first cohomology, and then to say that L of S, this joint minimal displacement, is equal to 0 means precisely that the cocycle vanishes in the first reduced cohomology. To say that little L of S equals 0 means that the cocycle is sublinear, so it has sublinear growth. To say that there exists a point where L of X vanishes means that the cocycle is a co-boundary, its cocycle is bounded. So all these notions have been studied a lot, in particular by Cornulier, Tessera, and Valette. And they, in this GAFA paper about 10 years ago, they have very nice examples showing that sometimes you have the equivalence between capital L of S equals 0 if and only if L of S equals 0 for some polycyclic groups. But sometimes you don't have this equivalence. Okay, so yeah, so for symmetric spaces, you always have that one is 0 if and only if the other one is 0. But it's not true in infinite dimension. Yeah, so this is the basic question I raised a minute ago. When, for which spaces do we have equality? And by these examples, you see that, I mean, these examples somehow show that you don't have equality in the case of flat spaces in Euclidean space or Hilbert space. So you need some kind of negative curvature, or at least non-positive curvature. And so when do you have equality? So the answer is yes for all symmetric spaces, for all Breuillard buildings, and all delta-hyperbolic spaces. Okay, but it's no for RD and Hilbert space. So I'll state now the main theorem that we have with Koji, and which we proved here at the institute. So here's the theorem. So suppose, there are three cases according to whether you are a Breuillard building, a symmetric space, or hyperbolic space. So suppose you have a Breuillard building, then in fact you have a much better. So not only do you have this Berger-Wang inequality, but you already have the equality before. So there is a k depending only on x, such that for every finite set S, you can realize the joint minimal displacement by an individual displacement of an element of a word in S of length at most k. Okay? So there is this eigenvalue that realizes the joint minimal displacement. In a symmetric space, you can't claim that. You can't claim that you have equality. You have equality only in the limit k tends to infinity, but not after a finite step. And the theorem is there is a constant c such that this holds. So this is the Bocchi theorem in the case. So Bocchi proved this in the setting of matrices. So for this norm, not for the cat zero metric. So for the cat zero metric, it's not, his proof doesn't work. You need a different idea. But this is essentially the analog of this theorem of Bocchi. And for delta hyperbolic spaces, finally, then you have this very uniform statement. So again, at the limit, you have equality, but this equality happens very quickly. So it's enough to take lambda 2. So remember this lemma of Serre, that if A, B, and the product A, B have a fixed point, then they have a common fixed point. So this is somehow a very quantitative version of this, that it's enough to take products of length 2, so in the elements of S, in order to produce an element with a translation length which is just as good as the joint minimal displacement of S. And this just as good is L of S minus constant times delta, and this constant is just an absolute constant. Maybe 100 is okay. It's just yeah. No. No. So yeah. So another way to formulate this in words is this. So this says that somehow that the minimal displacement grows. If it grows at a certain rate, then there is a reason for this. It's because there is a nice hyperbolic element which grows at the same rate. And you can find this hyperbolic element already in a bounded ball of length at most k of x. Okay. So you see a translation of this inequality here or there is this, right? So that if you look at, you can find this g in a short word in the elements in S to the k, and L of g to the n will grow just like L of S. So this is responsible for the growth. So it's a little bit in the same spirit as this Gleason lemma, that you can find an element whose powers are already responsible for the growth. So unfortunately, the proof that we have for Breuillard building and symmetric spaces is not geometric. The proof is, so it's a different proof from, it's not like Bocchi's proof, it's a different proof, but it still uses algebra, still uses the fact that, you know, Breuillard buildings and symmetric spaces are linear, so they have some faithful linear representation, and it works for all Finsler norms from Anne Stork, not just the L2 cat0 metric, but also other norms. In fact, it's enough to prove it for SLD because of the in the cat0 setting. It's enough to do it because somehow the minimal displacement is always achieved on a convex subspace. So you can embed every symmetric space as a totally geodesic convex subspace of some SLD. So the proof reduces somehow to a matrix computation, but the advantage of our proof compared to Bocchi is that it gives a better constant. It does not use this Prochési theorem, so k of x becomes just d squared, where d is the size of the matrix, and the constant is effective, whereas in Bocchi somehow it was relied on some topological arguments that can be made effective easily. So so here's but still an open problem is to find a geometric proof of this. Even if you go back to Parrot's theorem about that I talked about earlier, that if you have a group of isometries of a building, all of whose elements are elliptic, then it has to fix a point. This, just to show this, there's no geometric proof. No. So in particular, I don't know if it holds for all the fine buildings. So that's the question. Can you do this for a fine building? Should be. But maybe this is, yeah, I don't know. Of course, for delta-hyperbolic spaces, we do have a geometric proof, and the proof is as Indira said this morning, the proof is a quasification of what you can do on a tree. Okay, so what can you do on a tree? Well, here's a souped-up version of Serre's lemma. It's a formula for the joint the joint minimal displacement. There is a formula. If you take any two isometries A and B in a tree, then the joint minimal displacement of the pair is the maximum of the individual, the translation length of A, B, and L of AB divided by 2. Okay, it's just the maximum, and it's not very difficult to show because you understand very well what happens in tree. You have axes, you look at the common perpendicular, and you understand exactly what's the translation, the displacement of a point x is basically twice the distance to the axis plus the translation length. So it's a small exercise to show that you have this equality here. And because everything is one-dimensional, you can actually show that if you take a finite set of isometries, then the joint minimal displacement is already realized by 2 of them. So it's enough. This is always also true. If you take finitely many matrices, then you also have this formula. And the reason for this is a kind of Helly theorem. So for trees, it's obvious that if you have a bunch of subtrees that are pairwise intersect, then they must intersect globally, right? So this, but in general, this Helly theorem is very useful. I think in this context, this was maybe first exploited by in a nice paper of Benson-Farb, that Helly theorem is useful here. So Helly's theorem, I remind you, says that if you have if you have a collection of convex sets in RD, and you know that any d plus one of them intersects, then they have a common intersection. And this is actually very general. There is a version of this Helly theorem where you don't need convex sets. You only need, there's a homological version where you only need that the intersection is a cell, and then so you don't. It's true. Very general fact. But it's certainly true. But what's key is the finite dimension, finite dimensional Casio space. Then you have this. And if you have a space with Helly D, then the joint minimal displacement is achieved by a subset of control size of most d plus one. Indeed, because you see that somehow the set of points that are moved less than something by an isometry, this is a convex set, okay, in a Cat zero space. So it's an intersection of convex sets. So that's very useful because you can always reduce the size of, even if you start with a very large finite set S, you can always reduce to a subset of bounded size. Okay. And for hyperbolic spaces, you have a quasification of this, what I just said before, which is this. If you have delta hyperbolic space, any collection of pairwise intersecting convex subsets, then if you enlarge them just by 28 delta, small enlargement, then they will have a common intersection. Okay. So yeah, so this is somehow how the proof of, I go back to the main theorem. So this is how the proof of number 3 here goes. It's a quasification of the proof for trees. It requires some work, but somehow it works pretty well, and yeah, so it gives this. So now I want to, in the last few minutes, to give some applications to growth, and this is what we had started to discuss maybe 10 years ago. So here's a corollary. So it's a uniform exponential growth statement for groups acting on hyperbolic spaces. So suppose you have a set S, it generates a non-elementary subgroup, so it doesn't fix a point or a pair of points on the boundary of a hyperbolic space. And so X there's no other assumption, it's just delta hyperbolic. And so then, and S can be any finite set like that. So, and then there are only two options. Either you almost fix a point, so the joint minimal displacement is at most C times delta, and C is a uniform absolute constant, which is effective, can be computed. We didn't really bother computing a precise bound, but probably just 100 is fine. And either you're here, or you can already find two elements, maybe in S or S squared, maybe a small product of two elements from S, which will generate a free semigroup. So you can find a pair which generates a free semigroup. So in particular, it has exponential growth. Okay. So here's a comment here is that if you take the infinite Burnside group, some infinite Burnside group, some you assume that a group generated by two matrices, two elements with every element has order p, and p is, let's say, a large odd prime, and you chop the presentation after a long. You delete all relators of sufficiently large length, of length larger than something. Then what you obtain, Olshansky proved, is an infinite group, an infinite hyperbolic group. So this means that there are hyperbolic groups whose Cayley graphs have balls, Cayley balls of very large radius, all of whose elements are torsion. Okay? So as we saw, this can't happen in a fixed linear group, but for hyperbolic groups, this can happen. So Of course, in this setting, the delta-hyperbolic, the delta of the hyperbolic group goes to infinity, okay, very quickly. And the reason is because of this. So in this setting, then, you will be in part 1 here. There will be an almost fixed point. So for hyperbolic groups, you can show that L of s to the n plus 1 is always bigger than L of s plus 1. So there is always at least some growth. So you're going to get out fairly quickly of option 1. And so this gives another proof of a result of Kubi that, you know, hyperbolic groups have uniform exponential growth. Yeah, and so this is a theorem of Besson-Courtois-Gallo from a few years ago, showing uniform exponential growth in the case when you have a group of isometries of manifold, n-dimensional manifold, with pinched negative curvature. And they show that the rate of growth depends only on the dimension and the pinching. But their proof was very ingenious and somehow, some part of the difficulty here is that you may have elliptic elements, and this was a problem for them. And in particular, their proof, they couldn't, they say explicitly in the paper that they couldn't really find a free semigroup. Okay, so they managed to show that in certain situation you could find a free semigroup, in another, then you must almost fix a point, and then they managed from this situation to build a certain harmonic map and derive exponential growth from that somehow. So yeah, so from our main theorem, we can recover their result. It's actually more general, but you see what's missing here to get. What's missing is you need to rule out option 1. Okay. So option 1 means you have an almost fixed point. So this rings a bell. It means you have almost fixed point. This immediately you think, well, Margulis lemma. Right? There should be a Margulis lemma. And indeed, there is a generalized Margulis lemma, which follows from this classification of approximate groups theorem by Greentown and me a few years ago. I'll remind you of the statement briefly. If you have an arbitrary group, arbitrary finite set, suppose you have this inequality on the size of products, where k is some number, then the set A can be covered by a bounded number of cosets of some virtually nilpotent group. And from there you can derive a Margulis lemma, which is very general, holds for singular spaces and just of bounded geometry in the sense I'm going to say. So using this, combining this with the previous theorem, we get with Koji the following corollary. So assume you have a delta hyperbolic space in which every ball of radius 2 delta can be covered by k balls of radius delta. Then you have uniform exponential growth, even you can find a free semigroup where the length here depends only on this k and not on anything else. Okay? Yeah, and so this gives, in particular, a direct proof of this theorem of Besson-Courtois-Gallo as a special case. And we are hoping that somehow this approach can be used to show uniform exponential growth in many other settings. And I'll stop there. Thank you.
So when you say that you would like to have like geometric proof, right, of your theorem, okay, maybe it's too good to be true, but can you reformulate it and somehow in terms of harmonic maps, saying going from some kind of symmetric space to a building?
Just for building, just for buildings, even for A2 twiddle buildings, I'll be very happy to see a proof.
No, I mean the target is a building, but I mean as a domain. So can you have?
The domain is any finite set of isometries of the building. But, you know, and so you can look at the graph that generates, the Kelly graph that generates. But
yeah, so what I meant, it's like more restrictive domain. Okay, maybe we can discuss it later. Yeah.
I think what's lacking is some better understanding of the geometry of buildings, at least for me. Right. Yeah.
Yeah, for the Breuillard part of your theorems, you really need a local field in a strict sense, or is it okay to have a non-discrete valued field?
Yeah, Hanselian valued field is enough.
So it works for non-discrete.
Yeah, it works for non-discrete. Factor.
Actually, I have a question. So your theorem covers symmetric spaces and buildings and delta-hyperbolic spaces. There's these other classes of spaces that geometric theories, some of them are interested in, namely modular spaces like triangular space and
Outer space, right. Yeah.
can you say anything there?
So we're talking with Koji. So this is still, you know, has been done at the institute in the last 2 months or so. And we're still discussing with Koji, and we're hoping we can, for example, recover Manga's results about the mapping class group acting on the curve complex. But yeah, outer fence, I'm not sure yet.
Okay, so any other questions? Let's thank Manuel.